Alright, so we're going to be covering the final topic of high school calculus, and that is the calculus of polar curves. And so this really just follows from how we have been dealing with calculus of special coordinates. So we've seen parametric, we've seen vector, and now we're going to deal with how to deal with calculus in polar functions. So a small brief reminder of polar functions. I kind of want to assume that you guys are familiar with it. If you're not, then you guys can ask. I can make a separate video on it. But we know a polar function is basically we get a function r, which is some function of theta. So we have r is equal to f of theta. And when we want to deal with calculus, often we're comfortable with things like written in terms of x and y, right? So when we want to convert any polar coordinate into a normal Cartesian coordinate, we can do it as such, where x is equal to r times cosine theta and y is equal to r times sine theta. And this just comes from the fact that over here r just represents a radius in like a polar graph, and to go into the Cartesian form where we're in terms of x and y, we know that this radius is at some angle theta, and so that's r, and we want to find out what the x value corresponds to and what the y value corresponds to given r and theta, and so this just becomes an application of trig. So that's how we got these two equalities. So we have a polar function, and we have the conversion into a Cartesian form, and often we're concerned with the slope of this function, and when we want to find the slope of the function, we want to find the slope with respect to x. So we want to find dy over dx. That gives us the slope of our polar curve. And the question is, how do we find that? And so these two sort of functions can hopefully remind you of parametric functions with the common variable theta. And that's what we'll be using to find dy over dx. So recalling back to a parametric video where I proved how to find dy over dx given a common variable, where here it's theta, we know dy over dx is simply dy divided by d theta divided by dx divided by d theta. And so essentially now we have a equality between the slope of a function and then the derivatives given the derivatives of like the x and y function. And one thing that's interesting over here is r is also a function of theta, so we can't just simply treat it like a constant. And so to find the exact formula for dy over dx, we need to do more work. So this is essentially the same thing as d over d theta of f of theta times cosine x, or cosine theta, divided by d over d theta of f of theta times sine theta. And then we can use the product rule to simplify this to f prime of theta times cosine theta minus f of theta times sine theta divided by, oh actually dy is, this is sine theta over here, and this is cosine theta. So let me fix that. This is cosine theta, and then this is sine theta. And so, yeah, the product rule still stands, but our numerator is going to be f prime of theta times sine theta plus f of theta times cosine theta divided by f prime of theta times cosine theta minus f of theta times sine theta. And so this is the formula for finding the slope of a polar function in in terms of x and y, because that's what our notion of slope is defined as. So given this, let's kind of work on an example. Let's find all the horizontal and vertical tangents of the function r is equal to 1 minus cosine theta. So if you recall what this polar function looks like, it kind of looks like this, like an inverse heart shape. function, and then yeah, like this. And so vertical tangents are like these kind of points over here where we would have a vertical tangent, and then horizontal tangents are probably like at these sort of points where we'd have horizontal tangents. And now we have to find all the values where we have a vertical tangent, all the values where we have a horizontal tangent. So we know that whenever dy over dx is equal to 0, that's a horizontal tangent. And whenever our denominator, where dx is equal to 0, that will correspond to a vertical tangent. And we also know that because this is like a polar function, dy over dx is simply equal to dy divided by d theta divided by dx over d theta. So whenever this is equal to 0, we have candidates of horizontal tangency, and then whenever this is 0, we have candidates of vertical tangent. Right, because the only time dy over dx will be 0 is when our numerator is 0, and it will be undefined with the vertical tangent whenever our denominator is 0. And so we have to find those out before we can actually find out the horizontal and vertical tangents. So finding the equations for x and y, we know x is equal to 1 minus cosine theta times cosine theta. And we can rewrite this as cosine theta minus cosine squared theta. Similarly, y is equal to 1 minus cosine theta times sine theta. And this is just like a property of property of polar functions. And we can rewrite this as sine theta minus cosine theta sine theta. So let's start with finding out our candidates for horizontal tangents. So the first thing we need to do is find dy over d theta, which is going to be cosine theta, and then we have to use the product rule on this side, minus cosine theta times cosine theta, and then the derivative of minus cosine theta is just sine theta, and then times sine theta will give us sine squared theta. And we need to find when this is 0. So we have cosine theta minus cosine squared theta. And I think one way to simplify this easier is to rewrite this in terms of cosine theta using the trigonometric identities. And so sine squared theta is just equal to 1 minus cosine squared theta. So I plug that in, get 0. And so this simplifies to cosine theta minus 2 cosine theta, or 2 cosine squared theta plus 1 is equal to 0. And then this is kind of looking like a quadratic function. One way to see that more clearly is if I let some function w is equal to cosine theta, then I get 2w squared plus w plus 1 is equal to 0. I can factor this by minus 2w squared plus 2w minus w plus 1 is equal to 0. And that simplifies to minus 2w times w, and then this will be minus 1, and minus 1w minus 1 is equal to 0. And then our factored form is now just minus 2 times cosine theta minus 1 times cosine theta minus 1 is equal to 0. And now this is just when cosine theta is equal to 1, and then whenever cosine theta is equal to 1/2. And I think one thing I forgot to mention is that we're only worried about the interval from 0 to 2 pi, just to make things simple. So cosine theta is 0 or equal to 1 in that interval when theta is equal to 0 or 2 pi. And then, sorry, this should be negative 1/2 because this will be plus 1, and then we're dividing by negative 2. And so cosine is negative in the second and third quadrant, so at 120 degrees, which is 2 pi over 3 radians, and at 240 degrees, which is simply 4 pi over 3 radians, is when cosine theta is equal to negative 1/2. So these are candidates for horizontal tangency. Now we have to find out candidates for vertical tangency. So that's where dx over dy is equal to 0. So first thing we want to do is find dx divided by dy. That is simply equal to minus sine theta minus 2 cosine theta, and then the derivative of that is sine theta, so this changes. We have to find out when that is 0. One way we can do this is, again, factoring out. In factor out sine theta, we get 2 cosine theta minus 1 is equal to 0. So this is 0 when sine theta is equal to 0, or when cosine theta is equal to 1/2. Sine theta is equal to 0 at theta is equal to 0 comma 2 pi. And then cosine theta is equal to 0 when, or 1/2 when we have pi over 3, so at 60 degrees, and then at 300 degrees, which should be, well, 300 divided by 180 divided by 6, 5, and 3, 5 pi over 3. So those are our candidates for a vertical tangent, and then again sine theta is also 0 at pi. So those are candidates for vertical tangent. So now we have like 3 cases, right? So dy, again, dy over dx is simply equal to dy divided by d theta, and then dx over d theta. So whenever dy over d theta is equal to 0, and then this is not equal to 0, we have a horizontal tangent. And that's whenever we have theta is equal to 2 pi over 3 and 4 pi over 3. So horizontal tangent at 2 pi over 3 and 4 pi over 3. So those are confirmed. Notice how at theta equals 0 and 2 pi, we also have a denominator at 0. So we're kind of indeterminate at that form, and we have to do a little bit more work. Vertical tangents are similarly when our denominator equals 0 and then our numerator is not 0. And that's when these cases and this, right? So vertical tangent at pi over 3 and 5 pi over 3. So the only cases we need to worry about are theta is 0 and 2 pi, and these are just the same case, right? Because dy over d theta is 0 and dx over d theta is 0, and well, theta equals 0 and 2 pi are the same angle. So luckily we only have to do computation for one part. But essentially we need to calculate what the actual derivative is as we tend towards 2 pi of dy over d theta divided by dx over d theta. And rewriting or plugging in dy over d theta and dx over d theta, we get, we get cosine theta minus 2 cosine squared theta plus 1 divided by minus sine theta plus 2 cosine, and I'm going to rewrite this as just sine 2 theta because I don't have to use the product rule in that case. And now I can use L'Hopital's rule and rewrite this as the limit as theta tends towards 2 pi of minus sine theta minus 2 cosine, or minus 4 cosine theta times sine theta, so that switches this plus to a plus sign, and then the constant gets removed, and then this becomes minus cosine theta plus cosine 2 theta times 2. So limit as theta tends to 2 pi or 0, we get this is just 0, this is 4 times 0, so the numerator is 0, the denominator, hopefully it's not 0, this is negative 1, and then cosine of 0 is 1 times 2 is simply 2, so we get 0 over 1, and that's 0. So means at theta is equal to 0, we have a horizontal tangent, since that's what our derivative, or that's what this limit evaluates to. So we have found out that indeterminate form as a horizontal tangent, so we can add these over here. And we don't always get the case that our slope's going to be a horizontal or vertical tangent, but we need to evaluate those indeterminate forms, and then we can finally conclude what kind of what the actual slope is. And we can look at this graph and kind of confirm it. Like at 0, we know that we're going to be at this point, right? And then similarly at 2 pi, we're going to be at that point again. So we have like a horizontal tangent. And then at pi, for example, at pi, cosine theta is -1. And then so our value is 2. So that's this point over here. So we would expect a vertical tangent, and that's what we're getting over here. So seems like our answers confirm what the graph actually goes out to. So this was slopes in polar curves, and I think I'm going to talk about other calculus components of polar curves later.